This meeting is being recorded.
Hello, everyone. This is another project highlight for Digital Rocks portal. So I welcome everybody back to a new semester, at least in the United States, a new semester starting. And we are very happy today to have Shan, Wang, and Tom Bultreys from Ghent University. And I'm going to briefly let them speak and introduce themselves in a minute. I just want to also, before they start speaking, I will introduce everybody here who is from the Digital Rocks portal side. So maybe everybody can just go, I'll briefly say the name and we can go around and they can just say what do they do and where they are. Anu?
Hi, everyone. My name is Anu Radhakrishnan, and I'm a PhD student at UT Austin in the Petroleum Engineering Department. My research areas are broadly in foam flow in porous media and gas flaring. And I also manage one of the curators for Digital Rocks portal, and I also manage the social media accounts. Nice to meet you all today, and excited for the presentation today.
Ankita?
Hi, everyone. I am a data scientist at Rio Tinto, which is a mining company. I'm actually based in Perth in Western Australia. And yeah, excited for a presentation today.
All right. Bernie?
Hi, everyone. My name is Bernie. I'm a PhD student at UT Austin as well. My research interests, I mainly look at electrical properties in carbonate rocks, heterogeneous porous media. In terms of Digital Rocks portal, I believe I'm a new curator. I don't know if I'm officially in that position yet, but I have also uploaded a lot of data and have done a lot of work on the back end. So
now you're official. And my name is Masha Pradanovic. I'm the PI of the Digital Rocks portal. So all of us that have introduced ourselves, and then some, we have two more engaged members, Hassan Khan and Javier Santos. We kind of do the work in the background, curating the data set and managing the newsletters, uploads, and so forth. And again, this is supposed to be a highlight of one of the projects. We realized that's a great way to actually start a research conversation. So this recording will be posted on YouTube. So Shan and Tom, would you please introduce yourselves? What do you do? And then start the presentation whenever you're ready.
Go ahead.
Hi, everyone. I'm Shan, a PhD student of Ghent University. I'm in the Department of Geology, and my research interest is the multi-phase flow in heterogeneous reservoir rocks. I also focus on the multi-scale pore network modeling with the data set from the flow experiment based on microcity imaging.
Hello, I'm Tom Bultreys. I'm since today an assistant professor at Ghent University. I'm one of the supervisors of Shan, and I work on pore scale imaging and modeling of mostly multi-phase flow in porous materials.
Congratulations. So this is also a celebration of the promotion. So take it away.
Go ahead.
Thank you, Masha. Hi, everyone. I'm Shan, a PhD student of Ghent University. I'm going to briefly introduce the dataset we posted on Digital Rocks portal, which was based on a steady-state capillary drainage experiment. The main goal of our experiment is to first quantify the porosity and the fluid distribution in the pore space, and then to perform rock typing for the sample. As many reservoir rocks have pore size distributions that are so wide, some pores can be fully resolved under the imaging technique that are micropores, while others are usually below the image resolution, which are the sub-resolution pores. With the microcity imaging, we could quantify the porosity of these two types of pores and also have a better understanding of the fluid distribution in the sample. Well, the rock typing is also called rock classification. It's crucial in the evaluation of rock heterogeneity. By incorporating the porosity and the rock type information in the current multi-scale pore network model, we found the model predictions could be significantly improved. So this is also one of the main achievements of our research. In this experiment, we used a very heterogeneous limestone sample. We drilled the sample into a small cylindrical shape with 6 millimeter in diameter and 20 millimeter in length. We used the two fluid phases in this experiment. The whiting fluid is the brine solution, which was deionized water doped with 25 weight% Ki. And the non-whiting fluid is the decking. I will call it oil for convenience in the following presentation. As shown in this diagram, we put the sample in the flow cell. At the bottom of the sample, there was a very tight water-white porous split. This porous split only allows the whiting fluid to pass through. Therefore, during the experiment, we made a dry scan in the beginning, then we saturate the sample with the brine solution. After that, we pumped the decking from top to bottom. Because of this very tight porous split, only brine could pass through from it, and the decking would occupy more and more pore space in the sample. So this is our drainage experiment. There are some microcity images from this experiment. So in the dry image, the black color is a micropore, and the gray colors represent sub-resolution pores with different porosity. So in order to quantify the pores, we fully saturated the sample with the brine solution, so the pores fully occupied by brine would be very bright. Then during the drainage experiment, for example, in this image, at low pressure, we found the decking invaded the pores with large pore size. With the increase of pressures, the decking invaded more and more sub-resolution pores. So this is the whole procedure of our experiment. In this experiment, we mainly compared the two rock typing methodologies to study their influence on the multi-scale pore network modeling. The first method is the porosity-based rock typing. With the dry image and this brine saturated image, we could calculate their difference to quantify the fluid distribution in the pores and obtain this porosity distribution map. For example, in this image, the red color represents a micropore, and the other colors represent sub-resolution pores with different porosity. Based on this porosity map, we could divide the sample into different rock types or flow zones. And then we used the porosity map and the rock type map to generate this multi-scale pore network model. We assigned different properties for each flow zone and also performed the simulation. Another rock typing method is a novel PCT-based rock typing. PCT is the invasion capillary pressure in our research. For example, in this image, each cube represents a voxel in this macrocity image. For each voxel, we could calculate their saturation at different pressures, and then we used a proc-scoring type formulation to fit these data points, which could give us two parameters, PCT and lambda. Lambda is related to the pore size distribution. If we do the fitting for all the voxels in the image, we could obtain this PCT distribution map. Then we could divide the sample into different flow zones based on this PCT map. And similar to the previous modeling method, we used the rock type map and the aforementioned porosity map to generate another multi-scale pore network model. Although the two models could give us similar macroscale properties, if we compare their fluid distributions on pore-by-pore basis, there are a lot of difference. For example, in this image, it shows the brine saturation distribution at low pressure in our experiment. The blue color is the brine, and the red color is oil. At high pressure, we could have another distribution. If we look at the predictions from the porosity-based model, it shows the predictions have a lot of difference compared with the experimental environments. But for the PCT-based model, its predictions improved a lot. Also, we compared other properties and calculated the errors. And finally, we could have these conclusions. Subrock type segmentation has a strong influence on the prediction of the pore-scale fluid distribution. This novel rock typing method performs much better than the porosity-based model because our calculation was based on the drainage experiment. This method will also be checked for imbibition and applied on more samples in the future research to make sure this method can be extended to the other complex reservoir rocks. Well, for the dataset was already available on the Digital Rocks portal, and where we uploaded the dry scan, the brine saturated scan, and modified scans. We also put our porosity map, PCT map, and the rock type maps available on Digital Rocks portal. People can use the data to quantify the complex structures of this kind of rocks, calculate their fluid distribution, and also use the data to do their model validation. So that's my presentation. Thank you for your time and attention. If you have any questions, we're happy to answer.
Thank you very much. And thank you also for posting both the data and the results, as you said, so it can be used for validation. Bertie, do you want to start off with questions?
Sure. I just had a couple. So when you were assigning your porosities, what kind of model did you use? So I assume that you based it off grayscale, right?
Do you mean this multi-scale pore network model?
Right. Yeah. So I see you have like
Yes.
the porosity map.
Yeah.
With all these different colors. So it looks like it's correlated to grayscale. So was it linearly applied, or did you use a different model?
Yeah, it's a linear mapping, I suppose. Yeah, it is. So the mapping is explained further in the paper, but yeah, it's a linear assumption, which of course can have some limitations, but it seemed here to give quite reasonable results.
And did you have any like mineralogy data before? Because
yes.
So you assume that like all of the intermediate like gray grains are micropores. So I guess that operates under the assumption that there's no other mineralogy.
Exactly. So yeah, this rock is kind of well known, sort of, because it's well, it has a nice complex pore structure, but it also is 99% calcite. So that helps with these kind of calculations.
I actually had a very quick question that is related to the same same slide, so I'm going to jump in. So did you use just the dry rock for this porosity map, or a combined both dry and wet state, like fully saturated?
Yeah. Yeah. We use the differential imaging method to obtain this porosity map. So the differential imaging method is the difference between the brine saturated image and the dry image. So their difference, on their difference, you can find the pores fully occupied by this solution, so that then you can quantify the micropores and sub-resolution pores.
Okay, excellent. Yeah, that's excellent. That also removes a little bit of noise, right?
Yeah, yeah.
So call it pore occupancy map. Anyway. Ankita, do you have questions?
Yeah, I think mainly from the imaging perspective and the image processing workflows that you might have used, did you find anything in terms of any challenges that particularly stood out in terms of image registration or, calibration of the grayscale images? What sort of, I guess, what sort of approach did you take for that?
Yeah, I think one of the challenges is the image normalization, because on different images, you will not have the same gray value. So in order to tackle this problem, we did the image normalization before calculate their difference. So the image normalization is based on selecting the two fixed values for the two known materials and setting them to the same value for different images and doing a linear scaling um, for them. So that means on different images, your darkest value and highest value, they are the same. So that way we could solve this problem.
Yeah, that took some trial and error to get that to work.
There's no science without trial and error.
Yeah. No, great. And what sort of software or I guess coding language did you use to do that?
For the image processing, I used a visual software.
Okay.
Yeah.
Okay, cool. Thank you.
Anu, do you have a question?
Oh, yes. I actually have a question about the slide with your with the core flood setup.
Yeah.
Are just curious about if you have the is your setup able to scan while you're running the core flood, or do you usually saturate it with brine or a decane and then you remove it and then scan it, do a micro CD scan?
Yeah, in this experiment, the flow cell was fixed on the stage, and the macro CT scanner would rotate to doing a scan, and so and then we didn't remove it from the stage. We just keep it there and saturate the sample, pump the decking to do this flow experiment. Yeah.
Okay. Well, that's really convenient because in our micro CD setup, I think when we remove the sample with injected fluid, it actually contaminates our micro CD scanner. So that's why I was really curious about what your setup is like. Yeah, thank you.
Yeah, so the scanner is really designed for in situ imaging. So we do, it's really a gantry-based system, which is quite unconventional. So the sample just remains fixed in place while the source and detector rotate around it. And we even use that to do fast imaging. So we image during the injection stage. So while the interfaces are moving and so on.
Okay.
Which in this case was not really the case. We took a bit more time to get really clean images. But in some other works, we've done this kind of fast imaging that's lower quality but higher time resolution.
Okay. Yeah, that's really good because it also lets you maintain your conditions. Like if you maybe set like a elevated pressure or temperature, right? Yeah. Well, thank you.
How fast can the front move in the latest images that you've taken that are actually kind of trying to monitor a dynamic state?
So the fastest we can image with this setup is 12 seconds per scan.
Okay.
So at sort of 12 micrometer voxel size. So then you would have to back calculate how fast the front can move. But yeah. And then of course it depends a bit, because if it's that only works on materials with rather well resolved pores at that scale, because of course those images, they are noisy inherently. So of course we cannot do that on any kind of material, but we have done some work on that. Yeah.
So I also have one additional question about the differences, with the understanding that voxel by voxel or pore by pore differences are always extremely difficult to look at. So one part of the differences, I think, comes from the fact that when you're doing porosity-based rock typing or any kind of pore sizes evaluation, they are where they are, whereas when you're doing flooding, there's a sequence and some of them occlude each other, right? So if you have very tight piece of rock ahead of some very wide spaces, well, those wide spaces will not be occupied because you can't get to them. So how much of that did you try to maybe incorporate or remove, or did you just let the method at the end judge who to come to first and that's it?
For this porosity-based method, actually, the segmentation of the different flows is kind of arbitrary because we don't have any reference to do this segmentation. So in the study, we tried to divide the sample into 2 rock types, 3, 4, and 5, and extracted their multi-scale pore network model. Finally, we found the model with these 3 rock types was the simplest model with which we could achieve a good fit with the experimental data. So this is also a weakness of this porosity-based method. However, in our PCT-based model, the segmentation was based on the K-means clustering method. So that means we could obtain some peaks in the histogram, and we used them as the ratios to do the segmentation, and the assignment of the properties for each flow was also from our experiments. So in this PCT-based model, we could reduce the influence of this user-based tuning or this user-based segmentation on the modeling. So that is their difference.
Well, you call it weakness, I call it reality. But so I'm laughing.
But you're right.
What it is, right? So how fast now, kind of looking to the future, for a future student, right? Then 5 years from now, you'd like the computer actually do this segmentation into 2, 3, 4, 5, and I don't know, 7 types on its own, and then present you, discard some outliers and present you with the results that are suggestion. But that requires a pretty fast moving through the process that you just described. Do you see that happening, or how long does it take right now to do all of this rock typing?
Well,
I want to automate. Where I'm going.
Yeah, because now it's kind of manual segmentation, and but it won't take too much time because you only need to select some ratios and doing the segmentation. Yeah.
Once you know how to do it, I guess it's a lot faster than what we did in the paper. But in the end, I mean, the experiment itself took what, a week or so to perform?
2 weeks.
2 weeks.
Yeah,
so it's 2 weeks of micro CT time, right? And that costs money. So that is one kind of potential problem with the method. So yeah, it's hard to say how much data you would need to train a model that then basically tells you the PCT map based on an image, and maybe a porosity map as input. That's really hard to say. But if if the amount of data that you need for that is quite high, which you might expect, then practical limitations today still are a bit that, we don't have automated experiments either, right?
Right.
And we don't have, going further than that, even we don't even have protocols that, one lab does one of these experiments, it probably looks a lot different than if another lab does that. And so those might be kind of things to look at if we try to bring this forward.
Everybody nowadays likes talking about machine learning, but machine learning or any kind of deep learning type of sequence, it does take time, and these are pretty large data sets. So it's not even that I'm suggesting any type of learning of that sort, though down the line, for sure, we can think about it. Maybe images should be smaller and even maybe some sort of a fast imaging. But even just from the automation standpoint, well, let computer pick 7 thresholds, present you with a result, right? And then let the computer make first 3 to 5 choices, if you will, and then just like you pick the best one and you go from there, and that could already kind of speed up the process, right? It's semi-automation. Suggesting.
And that's in practice, that's how we work a lot of the time if we're doing time result imaging. Right? It's kind of like semi-automated, because if you have 100 time steps, you cannot segment them one by one. So
right. All right, excellent. So does anybody have any more questions? If not, thank you very much for presenting your project. Data can be found on Digital Rocks portal, so we invite everybody to engage. So if you like something about this method, go and try it out, or don't like something about this method, go and try out, and the data is posted for validation and comparison, and that really improves the science behind it. So thank you all once again, and this video will be posted in our next newsletter. Thank you.
Thanks for having us.
Thank you.